Faraday's law states that a magnet moving through a coil of wire will induce a current in that coil of wire. So we thought, how could we visualize this? What we're going to do is use this frisbee to represent a bar magnet, and quite conveniently, this handrail represents a coil. So we'll throw the frisbee through the handrail to demonstrate Faraday's law. A changing magnetic flux induces a current in a wire. If the frisbee has a constant magnetic field and we throw it through the handrail, the magnetic flux through the handrail will change. This will induce a current in the coil. To determine the direction of the current, we can use the right hand rule. If our thumb points in the direction in which the frisbee is moving, the other fingers will point in the direction of the current. So if the frisbee is moving in the other direction, the direction of the current will change. If the frisbee is not moving, there won't be an induced current. This is because the magnetic field is not changing. In 1831, Faraday showed that a changing current in one circuit would induce a current in another nearby circuit, caused by a changing magnetic flux through the wires. Faraday was able to demonstrate his ideas pictorially using field lines. But Faraday was a self-taught scientist, and even though he was a great experimentalist, he lacked the mathematical skills to fully describe his discovery. Maxwell combined all of the known electromagnetic phenomena and mathematically defined them in 20 equations, which included Faraday's discovery. Oliver Heaviside, an English mathematician and physicist, condensed them into 4 neat equations that we use today. By doing this, Heaviside was able to formulate the equations based solely on electric and magnetic fields. This demonstrated the symmetry between electricity and magnetism. Ampere's law describes how a changing electric field causes a magnetic field. Faraday's law describes how a changing magnetic field induces an electric field. From Faraday's original experiment, he realized that it was a change in magnetic field that induced an EMF. He then noticed that it was a change of the magnetic field through an area, which is magnetic flux, that induced an EMF. However, a part of the equation was still missing, and this is Lenz's law. Lenz's law states that an electric current induced by a changing magnetic field will create another magnetic field in the opposite direction. We can see this in action by dropping a magnet down a copper tube. As it falls, it induces a circulating electric field in the tube, which in turn must generate a magnetic field. If this new magnetic field was in the same direction as the magnet's magnetic field, the two magnetic forces would combine. However, due to conservation laws, we know that this can't happen, and therefore it must act in the opposite direction, which in turn slows down the falling magnet. We now see that the EMF is equal to the negative change in flux. The EMF can be expressed as the rate of change of the integral of magnetic field over a surface area S. Further to this, the EMF can be expressed in terms of an integral of electric field around a closed loop C. Therefore, combining these two expressions, we get the most general representation of Faraday's law in integral form. The equation can also be expressed in differential form. This shows the curl of the electric field, which is the field's tendency to circulate around a point, is equal to the negative of the rate of change of the magnetic field. Here we have a bar magnet and a coil of wire connected to an ammeter. Firstly, let's prove that a current is actually induced in the coil by passing a magnet through it. We can see that by passing the magnet into the coil, the needle on the ammeter deflected to the right, indicating that a current flowed through the coil in one direction. While the magnet is stationary inside the coil, the needle does not deflect in either direction, meaning that there is no induced current. In order to induce an electric field in the wire, we need a change in magnetic flux. A stationary magnet will have a steady, unchanging flux. Removing the magnet from the coil results in the ammeter needle deflecting to the left, indicating that a current has passed through the coil in the opposite direction. If the magnet moves through faster, or there are a greater number of coils, the induced current will be larger. So what happens when our magnet is not enclosed by the coil? A current is still induced, however it is smaller because there is a lower flux density cutting through the coil. This equation underpins many modern-day applications, including induction stoves, electric musical instruments, transformers, and induction torches. Faraday was a pretty cool guy, wasn't he? Hi Jonas.
Had it all up.
How's it going? Much love.
His head on.
Yeah, but you remember you don't want to get this
Yeah.
in as